Dadhich. I work as a senior data scientist at Tricog, and today I'll be exploring an in-depth session. This will be a tech side of more majorly what machine learning engineers, AI engineers, or data scientists do in day-to-day life, but specifically for cardiac care or ECG. Raise of hands who have taken an ECG test before. I hope it's all normal. Great. So there won't be. So today what we'll talk about is what is ECG and heart conditions, challenges often faced in an ECG analysis, foundation models. I know Arvind gave a very good talk earlier, but I'll give a brief overview of what it is. And large-scale data set that we have developed, we have used self-supervised learning, and will provide some results in analysis that you can also relate to in the open source data set. So the heart has different sorts of muscles around it and different points of electrical signal generations. So these are the different areas where the electrical signals are generated in the heart, and these get overlap, and on the body surface, it looks like this, PQRST, that is a general convention for a heart signal. And how do we capture it? We have an ECG machine that puts few electrodes on the chest, right arm, left arm, legs, and an electrical activity is captured on a paper, on a digital form, from the body surface. So that's the basic principle of an ECG. But what does it measure? It measures different sorts of heart conditions. There are basically three types of these. Circulatory system dysfunctions, which is basically if there's a blood flow irregularities, structural issues in the blood, or there's an electrical system malfunction, or disruption in the heart rhythm, which is basically lub-dub sound that you usually hear, and that happens because of the electrical system working. And the muscular impairment. The muscles are not even functioning properly. An example of this condition you can see on the right-hand side. The first graph is the normal heart signal, or normal ECG. On the right-hand side is an abnormal ECG, which is ST elevated myocardial infarction. This is commonly called as heart attack. You can see the difference in the graphs. So there is a small ST portion in the normal, which is not the same in the abnormal section. So this is one way to identify one of the type of the heart attack. It's not always the ST elevated. These conditions can be as rare as 0.5% in general population. So it's not widely prevalent, you can see. So general estimate, how many heart conditions that you can think are there that doctors usually diagnose? 10, 20, 30, 40, 1,000, 100? So usually there are about 100 conditions that doctors diagnose. And multiple conditions can be present in a person. It's not like they have present one of them. So they use ECG is the first test that they do, which is low cost, widely available, and it's non-invasive. You don't have to pierce someone's body to get this data out. And on the right-hand side is a sample ECG capture that we do on Tricog. The format is 3x4. You have 12 leads, and one of the long lead is present for the 10 seconds. Other leads are present only for 2.5 seconds. A doctor sees this and diagnoses this. And the doctor usually use different sorts of rules and sort of experience to diagnose this. I wouldn't say it's only rule-based. If that was, then everyone would have perfectly diagnosed everyone. But there are a lot of variations in it, and there are challenges in doing this. So the first is variability. Even in the patient, the ECG varies over the years. 30, 40 years, you have different ECG patterns. 60 years, you have different ECG patterns. Intra-patient. So ECG is like a biometric for a person. So not every two person will have the same ECG. They have minor variations so that you can easily identify doctors up to the extent they can even recognize a person if they have seen the ECG before, without even giving any of the patient information. There's a noise and artifacts. Even if a person is just moving, the body fat is moving, they breathe out a lot, they additionally adds noise and artifacts in the signal capture, and the signal becomes too noisy to do anything. Complexity, we have 12 lead as standard, but there are Apple Watches, Samsung, which give single lead also. And interpretation, there are, as I've said, that there are certain conditions which are about 0.5% prevalent. So for the doctor to train themselves for these 0.5%, it becomes a bit difficult. And also there are minor abnormalities or rare conditions which have have subtle changes in the ECG, and they have to be very precise on that. So we assume that the foundation models that Arvind has expertly given a talk before can solve this problem. What we define foundation models as deep learning models that are trained on large-scale data set and are adaptable to wide range of tasks. You can see, if you have heard of foundation model, one of them should be there in this graph: Stable Diffusion, DALI, Llama, GPT, OPT, and there is a MedPalm also for medical domain. All these are categorized under the foundation models, but we think that there are foundation models needed for ECG also. These are the deep learning model trained on large-scale ECG datasets, which can be fine-tuned for specific tasks. What are these tasks? We categorize them into 4 sections. One is screening, which is detection of asymptomatic diseases. So a lot of patients not always feel some symptoms when they are uncomfortable. So ECGs can do that, diagnose. The diagnosis is a very straightforward. You're given an ECG and detect one of the conditions. Prognosis is estimation of when the body will not work properly in the future or a progression of a disease. And the treatment is to suggest if certain drug is even providing the right treatment for the heart or for the general body. So these are the 4 different tasks that we think that the foundation models will help in the future for using the ECGs. And moving forward, there is a huge need of foundation model because the critical heart diseases, for example, AFibs, ventricular tachycardias, have very low prevalence rates. So even if you have to train a model, you have to capture like hundreds of thousands of ECGs in general population to have only few samples of these to train a model. Label data as such will become very difficult. You need an expert to label these ECGs, as even I have done so much of training of these ECGs, I can't read it. I need an expert guidance for this. There's a lack of large-scale publicly available data sets. In the bottom, I've given what are the publicly available data sets: Mimic4, Code 15, PTB-XL. There is some issue with each of these. The maximum I've seen is 800K, but it doesn't have labels. The second best is 345K, which is not enough. And 21K is the most common one, which has cardiologist availability. And coming forward, we are getting a lot of multi-model models, and creating a foundation model for ECG will also help combining ECG with other modalities like an echo or MRI or CT scans. And the last, not the least, these embeddings can be used for a general ECG and have more robustness across even low prevalence rate diseases. So what we have done is we have about 20 million digital ECG. The RICOG has diagnosed 20 million patients till now. We have 20 million digital ECGs in the bank. We have de-identified it, removed any sort of patient health information, and we have provided quality check by sanitizing the data and created a 4 million TRICOG dataset. I call it plus because it's still being developed. There will be more millions attached to it in coming few months. Right now we have 4 million as usable, trainable datasets. And this is not, no other dataset in the world, in the open source world, is even close to this. And this is expert annotated with majority of it is India, Southeast Asia, and Africa demographics. None of these above dataset has India demographics. We have in this dataset about more than 100 plus conditions, expert annotated. We have devices such as GE Max 600, Mac 2K, TRICOG, vCardia, which is our own ECG machine, and across multiple age groups that you can see. Devices are very crucial because healthcare signals depends highly on what kind of device you are taking up. So how do we build the self-supervised foundation model? We use self-supervised learning, which is 2 phases. One is a pre-training task. The second one is the fine-tuning task. In the pre-training task, we use the digital ECG. I know this is an image, but we're actually using signals. It's not an image as an input. We transform them into 2 different pathways. Both the pathways goes through a foundation model, generates a representation, and a final projection out of it will generate a final embedding, Z. The Z from 2 different pathways should exactly match in an ideal world because they are from the same input. So the task of this pre-training is to minimize those distances. Since we are transforming, these embeddings will not be the same. We will train this foundation model which tries to minimize the distance between ZA and ZB. And once this is trained over a large data set, This foundation model can be used for fine-tuning as an initialization or a frozen block that can further add a classification block and take presence or absence of a disease. That's the next slide. Please hold on. The question is, what is the transformation? I'll show you. Just bear with me for a few slides, I'll show you. So that's how the two phases of general self-supervised learning work, and this is how we are training a foundation model. This part, the bluish region, is we call as foundation model. These can be different sorts of architectures, ResNets, transformer, which all these we have been developed. What kind of transformations we do? So in images, you have a certain set of transformations, but those are not valid for this case. This is the ECG. Even if you reverse the ECG, it will completely change. It's a lead arm reversal, which is not a correct way of capturing. So you have to be very precise of what kind of transformation you do so that the diagnosis doesn't change. So we use baseline shift, which is small shift of a certain part of the signal. These baseline wander, which is addition of a kind of a cosine wave over the whole wave, a power line noise, which is like a huge noise in the ECG, and a cutout is randomly dropping some region. All these transformations are naturally present in the ECG. If you look at hundreds and thousands of real practical ECGs, some of these will be present there. So it's not like we are forcing some of these. It's a natural transformation. We are forcing in ECG to have these natural transformations. The transformations are not limited to this, but these are the most common that we use. I hope I answered your question. It's not altering the pattern. Doctors can still diagnose the same way.
Why are we doing these transformations?
In order to learn, force a model to learn without labels. So in the pre-training task, there is no labels attached to the digital ECG. We are using all the inputs. We are using all the input ECGs as two pathways, and we have artificially created this transformation such that the model forces to learn some patterns which are common to the ECG. In spite of the transformation, the model will be forced to learn the core features for the ECG. That's why we do transformation. Otherwise, you need labeled dataset. That is a simple fine-tuning task. If we have enough labeled dataset, we don't need this. We can directly use labels and train for it. But we don't usually have in healthcare all sorts of labels for a specific disease. If you want to detect normal, it's easy. But normal is not usually required for patients. They want to detect diseases which are rare to find. Yes, please.
To predict the disease risk only using the ECG. You mentioned ECG patterns change based on the age as well, and other comorbidities can change the disease.
I'm sorry, I didn't quite understand the question. Do we predict based on only ECG, or do we use other information? We can predict only with ECG. The age and gender, all these factors are ingrained in an ECG. There have been research that they can detect gender from ECG itself. So those factors are ingrained in ECG. We don't need a separate information. We have tested empirically. It doesn't change the performance.
What are those factors you said, age and gender?
These kind of things like age, gender, and basic comorbidities like are you smoking, do you have any sort of symptoms, those kind of things are ingrained in ECG. They are not visible to naked eye, but deep learning models can understand those kind of patterns in the ECG, and there are research that proves that. So we don't need to have separate information passed to the ECG to add these features.
And the pre-trained model already has been trained on such information?
No, it starts from scratch. We train it on a large scale 4 million data set. We assume that this information will be present in the foundation model when it is trained on 4 million set. And we'll see that in the later results that it's been.
What are architectures you'll be having this CNN and
I'll show that. I'll show that in next slide. So I'll first explain what kind of, there are lots of different self-supervised learning methods. I'm using a deep metric learning type of architecture for self-supervised learning. In deep metric, you have 2 pathways. Both the pathways should be as same as possible at the end in the embedding levels. And what is the kind of loss you can do? You can basically just do mean squared error between the two embeddings, but that doesn't work. We are using VicReg, which is one of the recent ways of training self-supervised learning. It just combines variance, invariance, and covariance at the embedding level, and empirically, this has been very good performing model across different sorts of tasks, even at the image level, even at the other audio and other levels. I'll not go into the details of this. Please go through the paper. It's very interesting research. So we did fine tuning. Now we have trained 4 million. There is no labels there. So how do you evaluate this fine tuning, pre-training of the model? You always need a label to evaluate something. So the only way to evaluate is do a fine tuning on a standard data set. So we use PTB-XL. I've shown that this is one of the open source. It has about 21K ECGs, which is quite less as compared to what we have. And this is from 18K patients. It predicts 5 different things: normal, CD, hypertension, MI, STTC. The definitions are here. Norm is mostly normal sinus rhythm, which is normal rhythm. CD, hypertension, MI are different sorts of conditions. These are the following ECG numbers for that. This is a multi-label classification. So one prediction can have multiple of these labels. It's not like I'm predicting one of the labels. You understand? A person can have MI and hypertension both. A person can have STTC and MI both. So we don't want to predict such that a person has MI and we are forgetting that he doesn't have a hypertension. Model should output all sorts of conditions that the person can have. And how do we measure? So we have trained this model over this data set. It's standard training, supervised fine tuning. And we trained it over 20 epochs using the foundation model we trained. So I'll show you one of the architectures that I've used. So we used VIT-S. VIT is a vision transformer. It was made for images. We have converted this to work with 1D inputs, which is our ECG. Our ECG is an input of shape 12 cross 5,000. 12 are the 12 different leads. 5,000 are the number of samples of the ECG. This is the basic architecture VIT-S with these parameters: 64 patch size, depth 12, number of heads 6. And we are achieving very high AUC. How do we measure this? Ideally, in a very ideal world, this should be like this graph. And the area under curve should be 1. But that doesn't happen always. The more this side of the curve, the better the model is. So we evaluate for each of these because it's a multi-label classification. Every output is like a binary output. And this is with foundation model.
Training data or testing data?
This is validation data set.
Validation, okay, thank you.
I have shown that we took this validation data set. This is only on the validation data set. And that one is the random initialization without foundation model. You can see that there is a huge difference in AUC of each of these categories with foundation model. And if anyone is looking at, I'll move on. I'll explore over multiple architectures. So this foundation model training or foundation model design doesn't always work. It's not like this VIT-S is the only architecture that we can use. We can use multiple of these architectures. The average AUC, for example, if I reduce this size of the VIT from 12 depth to 6 depth, if you're getting confused on VIT, it's a very standard architecture. Later on, you can look at in the Google and you'll get why there's a 12 depth, what are number of heads, and so on. So if I reduce the depth with foundation model, the average AUC still holds. And furthermore, with more architectures, ResNet style of architecture, I know if many of you have seen ResNet. ResNet was trained for 2D images. We use it 1D for ECGs. That still holds 0.904. Above 0.9 is a very good model. Below 0.9 is not great model. But you have seen that ResNet 1D34 is 0.858 only. All of these architectures were first pre-trained on 4 million set and fine-tuned on the smaller 21K set. 21K set is a representation of what kind of data set we play with in ECG world. We don't usually get that many of labeled data set. What happens if you have much lesser training data set? So I compare it with, I put my training set 50%, randomly selecting only 50% of the patient, which turns out to be about 8 or 9K only. Even with 8 and 9K, my AUC is 0.9 for the best model, VIT. But if I reduce 25%, it drops. But if I don't use foundation model and directly use random initialization, with 50%, there is a very bad accuracy. This is even worse than the 25% trained model. So if I have a foundation model, very less data set still outperforms direct training of the model from scratch.
Why the model is not picking good accuracy towards hypertension?
Because the numbers are small, first of all.
Data itself
Data is smaller.
So what about false negative rates?
Good question.
Because I would think that for a ECG world, right, a false negative is far worse than a false positive.
That's true. That's true.
Yeah.
For today's scope, I didn't add that. You can reach me out. I have all that data also. This exercise is only to show the capabilities of foundation model. These are not to deploy it in real world. We will further have to fix the model to have a real world capabilities. I use this data set because it's publicly available and it's easy to relate with. And majorly is to evaluate foundation model because there is no other way to evaluate the foundation model.
So without a physician, can we assess by using this model
Yes.
any compounder and a non-qualified practitioner?
Yes, we have a production deployed model
Okay.
which assists doctor.
With the assistance of the doctor?
Yes.
Even with this 94% accuracy?
This is not the model.
Not such, okay.
This is only to show the performance of foundation model. We use our own internal data set to train and fine tune for that.
Is there any variation between male and female heart rhythms?
There is.
Then how it is coping up model?
That data I don't have, at least for this sake.
Okay.
But you can definitely reach out later. Yes, please.
This personal health information is sensitive, right? So how would you get more data to train your model? It's very limited data which you have, right? So it's not commonly, in India maybe you can easily get, but in other countries this personal health information is not openly available.
We don't need personal health information.
The health records like the ECG, right? So how?
ECG records are very hard to find, but PHI is a different thing. PHI means that you can identify the individual in the real world, which we don't want.
But health records are not easily available, right?
Yes.
So how would you arrange for those?
Because we have 20 million digital ECG bank, we have enough data to train on the patient. We have worked about 10 years to build this kind of data set.
The data bank which you have?
The data bank we have. We work very hard to get the high labeling rate, doctor's performance very high, and we work very hard to remove any sort of PHI and sanitize. It's not always like everyone gets the best quality ECG. There is quality levels on the ECG levels also.
It's ranging for a decade? More than a decade data?
This data is from 2019 till present.
Acha, only
We are working for a decade and more, but the data I have used right now is 2019 and present.
Okay, over the period of years, decades after decades, is there any change in that heart?
There is usual. It depends on the patient. If a heart failure patient, the
Then
ECG
model has to take care of those things also.
Yes, really. Yes. Yes, ethnicity is placed on major role. Most of the models have been trained on white population or Caucasian population. We have focused mostly on Indian demographics or Southeast Asian region. And diagnosis is more specific to Indian and this region. We haven't tested it out as compared to the Caucasian world or white world.
Since you have 4 million data points, there must be some class management. So how do you deal with it to fine-tune the model?
Fine-tuning I'm doing on the open source data set. That is not in my control.
Right.
Whatever the data is available, open source, I have fine-tuned. Pre-training, I'm using 4 million. The class imbalance, I'm hoping that it is not there. There are rare conditions there. It has general population prevalence. Some conditions are 0.5%, 1%, 3%. Those kind of things are there. But in fine-tuning, in a real-world deployment, we have to specifically curate for that. We need to have good enough rare classes so that it doesn't get underfit for those.
So you mean like in pre-training you are passing all of these
Yes.
ECGs, right, to come up with that embedding vector?
Yes.
That is like foundation model. But when you are creating or fine-tuning this classification model, right, where I see some 4 or 5 classes.
Yes.
So there might be like class imbalancement in this, right?
Yes,
across
there
4
is
million.
class imbalance. You can
Right.
see that.
Right.
There, hypertension is not there. And
Right.
all those
Any methodologies you have explored in the transformer side?
Right now, I have not explored that. I was
Okay.
major focus on getting what are the performance I can derive from foundation model.
Okay.
Not specific, since I am not going to deploy this model. This is
Sure.
only to judge the quality of the foundation model.
All right. Thank you.
Thank you. No. This has like about 80% of this, which is about 18K something in the training set. So 18K is, luckily I've got this. In real, for specific classes, I don't always get 18K sets. So what happened, the task was done to evaluate what happens if I don't have 18K. What if I have only 50% of the training data set? How much is the performance change with the foundation model? There is minor drop in the performance, even with a half the training rate. But if I reduce to 25%, which is about 4 or 5K, then there is a drastic change, and that's where the progression starts decreasing of the performance.
Hi. So I had one question. In the beginning, you told, right, that you are collecting these ECG signals from different devices, right? So each device will have its own different errors, right? Accuracy and precision. So how do you cater to those kind of errors while you fetch the data?
There are, I wouldn't say it's an accuracy precision, there are filters on the device, which filters the signal for a good quality output of it. G has its own, Tricog has its own. All these are standardized by a regulatory body. The output, whatever they are giving, is within the precision limit as prescribed by the regulatory body, so that the doctors don't make a mistake on it. So I don't have to take care too much of it because it's been approved, and I assume that they are working with that approval in a sense. So I don't see it's a major challenge right now. At least on the ECG side. On echo front, there is all this sort of things, but on ECG front, this is not a major hurdle. Yes, please, sir.
So from 20 million ECG dataset that you had, you reduced it down to 4 million, right? So what was the criteria for kicking out some of the ECGs? Was it just quality issue, or was it because this is a POC and you didn't want to use the entire data set?
No, the reason is to get 4 million is 4 million was we could have done till now. Hopefully we will be able to do 20 million soon.
Oh, okay, so it's a training data.
That's why I said plus, because it's still in progress and we are able to.
But your original library has 20 million ECGs,
yes.
right?
Yes.
Yeah. All right, yeah, thanks.
Ethnicity is a factor. What is the distribution of ethnicity? Why do we have a separate model for ethnicity?
That's a good idea. In the fine tuning, we can have ethnicity specific models, but pre-training we assume that it will be more generalized. We don't have to pre-train every time and again because it's expensive task, and we can't always pre-train on large scale data sets. Mostly it's 90% is India, 5% is Southeast Asia region, and 5% or less than 5% for Africa. Let me finish 2 more slides, then I'll take more questions. The question is foundation model always better? So I've shown that all these models were performing better, but when I used ResNet 1D34 and directly trained without using foundation model, it performed much better. The reason being, the data set is small, 21K is much smaller, and the model is also very small, so there are very less parameters to be trained on. And so smaller architectures can't be used for foundation model training. That is what my takeaway from this is. And finally, where do we use this? So it can be used in improving the performance of assistive diagnosis. Fine-tuning can be used to reduce computation.